All right, next example, optimization. In this figure, we have the curves of y equals the square root of x. So that is clearly this red function graphed here. And then we have a rectangle. Oh, sorry, skipped the rest of it. X equals 9. So that appears to be this vertical line. And y equals 0, which is, of course, just the x-axis. So we have these three curves, and you can tell that they kind of make an enclosed area, right? And then inside that, we have a rectangle with vertical sides at x equals a. So this is not set, it's changing, and x equals 9. So because the 9 is given as a constant, this side's going to stay here. X equals a, it's not given as a constant, which means this is the one that could change. So you could think about if the a was over here more, then my box is going to look like this. Right? Or of course, if the a was over here more, now that is my box. So you can see how the size of the box will change as the a value changes, which makes that top float along that curve. Okay, we'll get rid of those pieces just so they don't get in our way. Find the dimensions of the rectangle having the maximum possible area. So it is the area of this rectangle that we are trying to maximize. So I need to try to come up with an equation. It might help if I labeled the sides. So maybe I'll make this side the W and this side the length, which makes the area equation very easy. However, I need to figure out what W and L really are. So let's dive a little deeper into each one of those and see if we can't write them in terms of A, right? Because that is the thing that we were given is changing. So let's start with the W. This vertical distance, how is that related to A? If my X is A, the W is equal to the Y, right? The Y value at that same X point. And since this curve is the square root of X, then the W will be equal to the square root of A. It's just the Y value on the curve, the square root of X, when X is A. What about L? So the L is going to be fixed on this end. It's always going to end here, but it's going to start at a different value depending on where A moves. So in this case, I'm looking at this distance right here. It might be easier to think of it right on the x-axis. So keep in mind, from the 0 to here is A, and from the 0 to here is 9. So what is the L equal to? It's 9 minus A. It's a change in X. Okay. So that gives us then that our area is the square root of A, maybe I'll write that as A to the 1/2 times 9 minus A, which is 9A to the 1/2 minus A to the 3/2. So now I have an equation for the thing that I'm trying to maximize in terms of one input variable. And that input variable is the location of the X where that rectangle would start. So take a derivative. I'm going to give you a chance to pause the video, take a derivative, find a critical number, think about endpoints, see what you come up with. All right, let's take a look. So I took a derivative, and then I just factored out, again, like we've done in many places, many previous lessons, I factored out a GCF. So I have a 9/2 and a 3/2, so I can pull out the 3/2. That would leave me with just a 1, or I guess a -1 here, and a 3 here. And then I pull out the lowest power of the A. So that leaves me with just the 3 here, because the A is already gone, and an A to the first here, because remember, this plus this has to give me this. So this minus this will give me this in terms of exponents. You can instead try to find a common denominator that works too. I think factoring is just as easy. All right, so this is going to equal 0. The a, this really, I guess I could have written this step right here. This would be like 3 times 3 minus a over 2 square root of a. So this doesn't exist when a is 0, doesn't help me, but it is equal to 0 when a is 3. So I'm going to throw that into a number line to check. And then I'm thinking about what are my natural endpoints for a? What's the least it could be? Well, 0. And what's the most it could be? 9. But once again, neither of those are viable options because I no longer have a rectangle. If it was all the way here at 0, I would just have a line. And if it was all the way here at 9, I would just have a dot. So neither of those are viable options. So we just plugged in some test numbers on either side, found that 3 was in fact a maximum. So then if my a is 3, that means my rectangle would be the square root of 3 by 6. Just plugging that a value into these two dimensions, because the question did ask me what are the dimensions of the rectangle.